Yeah, so welcome everyone, welcome to this week's Crunch Seminar. Our first speaker is Roberto Furfaro from University of Arizona. Professor Furfaro is currently a full professor at the Department of Systems and Industrial Engineering and the Department of Aerospace and Mechanical Engineering. He has served as PI and co-PI of numerous high-impact research and development grants over the past 15 years. He's also an AIAA Associate Fellow and American Astronautical Society Fellow, Class 2022. So without further ado, let's welcome Professor Furfaro. Professor, you may want to start.
Yes. First of all, let me reinforce the thank you to George and all the Crunch group for inviting me, and also give an opportunity to present some of the things that we've been doing. So as you see, I'm going to do a little bit of an excursus the way we think about these problems, right? And we go from real-time optimal control to stiff kinetics, chemical kinetics equation. And, keep in mind that, we come from engineering, right? So, we're, I would say, fluent in math, but we're not applied mathematicians. So we take a different kind of approach to these problems. And I want to share it with you so you kind of understand how we think about these problems for potential even real-time application of the physics-informed neural networks, to specific problems. Now, my field of research and actual application is generally aerospace. I've been involved in space missions, and currently I'm actually recipient of a big grant from the Joint Hypersonic Transition Office, right, to apply machine learning to guidance and control of hypersonic vehicles. And we're trying to scale this up. That is, go beyond the formulation, mathematical formulation and theoretical part to real application. I want to give you an idea about how we go about this, and I'll have a chance. I'll give Mario the floor, you a chance to specifically then talk about one of the things that you might be very interested in, which is the stiff chemical kinetics equation, how we solve it in the recent paper published on Chaos. Okay. All right, so this is a little bit kind of the outline. As I said, we're going to go from optimal control and discussing the Pontriaggi neural network with the aerospace, which is the physics-informed application, for for optimal control and aerospace example, and then we'll talk about stiff ODEs, and our framework that we put together to solve this kind of problems. Okay. All right, so let's start about a real-time problem, which is autonomy of general aerospace systems, right? There is a new paradigm that is coming on into this guidance and control community, which is computational guidance and control. And the new generation of systems that want to fly need require new computation and learning methods. And generally, the overall idea is to integrate in the same framework of data and physics. I come from, as I said, aerospace engineering background. We're always trained on, more or less deterministic system where we write equations, Newton's laws, and so on. And we try to develop, for example, control methodology based on that. And for the longest time, this community has been very skeptical about the power of neural networks, simply because they say, oh, we don't know what they do. Then when the physics-informed ideas came on, people get more excited because the idea of having data regularized by physics is very appealing, because, flying aerospace systems is extremely hard in the sense that it's expensive, any failure, results in millions of dollars of, expenses. And, and so one of the questions that, yes, you can improve a lot of performance using, for example, physics-informed neural network, but how do you know the behavior of the system? How do you certify these systems? Okay. All right. So let me give you an excursus of how this goes, how people think about solving this control problem, right? So the general mathematical formulation of a control problem is this, right? Basically, what you want to do, you want to minimize the cost function, usually comprising two terms, subject to some constraints. Constraints are the physics, represented by the ODEs, tells you what is the equations of motion, you give the initial condition, you give control constraints, you can have final time or state constraints, and whatever, okay? And so now you formulated this problem, you come maybe from first principles of physics, and then you say, okay, I want to solve it. I want to find I want to find the controller such that minimize this cost, okay? So there are two methods of solution to do this. The first one is direct transcript. It's called transcriptions, right? Basically what you do, you discretize your problem. You take your continuous problems, you discretize both state and control. For example, through the pseudo-spectral methods, you expand X and U in some polynomial basis. And then basically what you do, you transform this problem in a nonlinear programming, finite, maybe it can be large, but for sure non-complex, and you try to solve it, okay? All right, one of the problems that you have with the NLP is that you have that this large nonlinear programming are non-convex, right? So global minimum are not guaranteed, which is a problem generally for if you want to do real-time application of these systems, right? Because you want to have a guarantee convergence within a certain number of iterations. Even fixed iteration actually is even better. So what people do, they convexify the problem, okay? Convex problems have a guarantee of a global minimum and polynomial time, and there is all a process people go through, convexify the problem, which means many times linearizing the equations. And usually because of the nonlinear nature of the problem anyway, you never end up solving one single convex optimization problem, where you have to apply a sequence of convex optimization, okay? For example, you guys are familiar with the SpaceX, doing a lot of effort in, for example, developing a platform like this, where they try to land on the ground or on a platform, right? And for the first time, they tried to do a real-time solution of convexification of convexified problem to try to online generate a landing trajectory and then close the loop to try to track this trajectory. This is an example of success of this approach, okay? All right, so let me go ahead, move on. Give me a second, it's not switching. Okay, so the other approach is which we're going to talk, and we're going to show how physics informed is applied from our perspective, is instead deriving the necessary condition for optimality. That is basically applying what it is known as Pontryagin minimum principle, sometimes called maximum principle, right? What you do in this case, you basically try to find the necessary condition which yields basically a set of differential equation. More specifically, what you do, you build this control Hamiltonian, which is done for which is built using the Lagrange continuous cost function, and then you put you define lambda to be the cost state, which is kind of the continuous Lagrange multipliers, right, for the continuous dynamics. And then the principle says that, right, at any time, select the control value that globally minimizes the Hamiltonian function of U, okay? And eventually what you do, you find an optimal control solution, right? From a practical perspective, usually at the end of the day, once you follow this approach, you have the Hamiltonian, you find the optimality, which is you take the derivative of H with respect to U. Eventually, you end up with a set of state equostate equation. And basically, what you do, you need to solve a two-point boundary value problem in state and costate. And we started, before even using physics informed, we started solving this problem. We apply something I'm going to introduce soon, which is the theory of functional connections, right? Which is integral part of our, PIN framework. So, this problem generally, two-point boundary value problem arising from the Pontryagin minimum principle are generally hard to solve, okay? And indeed, this is a little bit, it's called Cursive Complexity. And basically, what happens is that due to the Hamiltonian nature of the system, the state and constant equation has a symplectic structure. And this gives you a quick example where you see, for example, what a one-dimensional problem subject to a quadratic cost function, you end up seeing that the state and constant equation has basically two eigenvalues in which one is positive and the other is negative. So solving a problem like that, is extremely hard from a numerical point of view. Okay. All right. So how do we approach this? Keep in mind that we don't want to just solve the problem. We just also want to find methods that can integrate data into the system, and second, can be deployed in real time. So we have to pay attention to both accuracy and speed of solution. Okay, so we came up with this framework, which we now call XTFC, stands for Extreme Theory of Functional Connections. And it's kind of a synergy between something called Theory of Functional Connection, which I'm going to be talking briefly next, and the standard PIN methods. And we believe it helps overcome some of the limitations of solving ODEs. Of course, even our framework, we don't claim that we can solve all sort of problems, right? But at least we know where we stand. We put this diagram together. On the right side, you see the PIN, using the single neural networks, maybe trained through the extreme learning machine. We'll talk about that. The other side, you see the PIN with the deep neural network and trained via gradient methods. Okay, so try to merge all this technique and try to see if we can take advantage of the power of the different approaches, and adapt to our problem. Okay. So theory of functional connection. Now, this was introduced by a colleague of mine, very good friends, Daniele Mortari. He's a professor of aerospace engineering at Texas A&M. The overall idea of TFC is basically to develop the so-called constraint expression. From a solution of the ODEs, the idea is to transform a constrained problem into an unconstrained one. Now, this is not a new idea, right? That people have been working on this, but I think that the theory of functional connection has been developed in a way that systematizes this approach. Okay, so systematically, you can build this constraint expression and transform basically the problem from constrained to unconstrained. And it's a very systematic way, it's very general, it applies to all sort of things, ODEs, PDEs, but it can go beyond. And you can do this, very much systematically. Now, the idea from Professor Mortari started because he asked a very simple question to himself, like, if I have how can I, for example, develop an expression that is general enough that represent any function that passes between 2 points, fixed points. The 2 fixed points are basically the constraint, okay, of your problem. And eventually, they developed, starting from that point, they developed theory, and they went on and on and on and generalized to different kind of problems to become some theory that connects not only, just functions and points, but potentially function and tensors and tensors. Okay.
Roberto,
now,
Roberto, I have a question. So the constraints could also be inequalities, for example, avoiding an obstacle.
It could be, yeah.
Okay, because here is you just have to go through points, but we have also
actually.
Go ahead.
Yes, actually, as a matter of fact, we haven't fully explored yet the ability to implement inequality constraints, right? However, the theory is there. He showed, for example, that he can develop he can basically, with this constraint expression, find all the functions, right? There are constraints to be within certain, boundary of 2 functions. Okay, we are not using that yet because we haven't exactly figured out yet how to do for an optimal control problem. Okay, so but this is a way of one rich area of research, we believe. By the way, Professor Mortari just wrote a book, okay, which is available, I believe, on available for purchase, and there's quite a bit of papers that we can, I can point you in the direction, especially for the inequality constraints. Okay.
Yeah. Thank you.
You're welcome. All right. So the other ingredients that we believe is also worth taking a look is this extreme learning machine theories. Now, PLM theory, approximation theory, is basically the idea is to basically represent the unknown function through a single layer neural network. At least at the basis, this has been also extended to potentially multi-layers or deep networks. But within a single layer frameworks, basically the overall idea is basically that the weights of the hidden nodes are assigned through a random distribution. Now, if you do this, you're basically representing a function as an expansion of random, functions, random function which have an activation structure and a neural network activation kind of structure. But there was this theorem that was proven that shows that basically, to the limit that you have a sufficient number of neurons, you can approximate any continuous function by assigning randomly this weight, at least in L2 sense. Okay. Now this is extremely important because you can do training without iterative tuning. Basically, what you end up doing is finding the betas on the outside layer, and you do this through a simple least square kind of solution. It is debatable if this gets you the best solution if you're talking about, for example, supervised learning. There's always, some claims that one has to be careful there. But from a ethical perspective, in terms of trading accuracy and speed, they are, in our opinion, extremely useful. Okay. All right. So now let's go through the different kind of approach, and you guys are all familiar with this slides we took from one of your paper here, and you're familiar with the whole PIN. I don't have to explain to you. The idea is that you have a neural network that approximates the solution. You take advantage of automatic differentiation. Eventually, you build the loss, which is a combination of the loss into the residual in the field, the residual for the initial condition and the boundaries. You build this, and then you go through some training to find the weights. Okay. We try to focus a little bit on the limitation, but keep in mind that we don't talk about limitation on a general terms, but specifically also with our kind of problems in mind, right? Now, one of the issues that we found, for example, that there is, there are, for example, you guys brought it up, one of your papers, that there are gradient pathologies because there is basically a competing problem going on between the gradients to try to minimize the loss of the boundaries and the one in the residual, right? And from our perspective, we found that some problems that are linear, generally if you apply gradient descents straight up like this, also you have, you treat it as a nonlinear, try to solve a large scale stochastic optimization problem. This is classical PIN, very effective, but the other things that people, while we were developing our XTFC framework, we found that in the literature, they already started thinking about the idea of, okay, represent the network through just a single layer random with the random nodes, and try to insert it into the equation. They come up with this PLM, framework. I mean, it can take advantage of, it can take out for specific, this is problem dependent, can take advantage of the ELM theory and maybe be more cost effective, but of course, accuracy depends, it's the problem, but it doesn't say anything about the boundary conditions. When we were developing, we were working with the Professor Mortari with the TFC problem. One of his students started thinking about, doing a deep network representation of the unconstrained function that come up after you apply that constraint expression. So basically, if you have a PDEs or an ODEs, you apply constraints, and then you apply the constraint expression. So once you have the constraint expression, you just represent the free function with the neural networks, and you can use a deep network. Now, in this case, in this specific case, basically you take care of the boundary condition. That is, you don't need into the system the loss for the that comes up from need to satisfy BC and IC because they are automatically satisfied, but then you still have to go through stochastic gradient descent or anything similar to do to solve the problem. Again, our XTFC came up with the idea to use now ELM to represent single layer forward network to represent G and come up with the possible solution. Now Enrico is here, is the first author of this paper that we put out last year in neurocomputing. What we found is that basically it's effective for a lot of problems. When complexity in terms of nonlinearity goes up, probably neural network might be better there, although the TFC piece holds the grounds in terms of representing, in terms of providing accuracy. Okay. However, XTFC is our main framework for PIN application for solving optimal control problem. And the reason is because actually we come up with this idea of Pontriaggi neural network that is basically our physics-informed neural network coupled with the XTFC to solve the two-point boundary value problem coming from indirect methods. Pontriaggi neural network also has been worked and devised by Andrea D'Ambrosio. I believe Andrea is here. He was a visiting student in my lab. We work on this quite extensively. He's currently at MIT, and he's been working on this quite effectively. The idea here is kind of you have a two-point boundary value problem coming from the application of Pontriaggi minimum principle. The first thing that you do, you build systematically the constraint expression. You use an extreme learning machine network to basically represent single layer, represent the free function. You build your loss. Okay, and then you find just the betas of the free function, the weights of the outside layer. And if the problem is linear, you do just one pass. If the problem is nonlinear, you do iterative least square, or some other additional methods, that can be implemented to solve this nonlinear problem. To keep the extreme learning machine, we do iterative least square simply because once you have the Jacobian, basically you can kind of iterate that, and we look at convergence performance there. Okay. Now, this is kind of goes to the idea that the Pontriaggi neural network can be applied to basically solve a control problem in real time in a model predictive control kind of fashion. So the way, I don't know how much familiar you are with that, but model predictive control, the overall idea is that you solve an optimal control problem in a time horizon. Okay, you optimize it, and you do it online in an iterative fashion. So you basically you close the loop by a sequence of open loop solution. Okay. And our idea is to basically continuously online train the Pontriaggi neural network using the extreme learning machine and across a certain time horizon. Now, the interesting part is that for most of the problem where you have state and constate equation represented by this equation, it turns out that you can do a fixed point iteration and show that there is a maximum time horizon under which the map is contracting. Okay, and so everything depends, of course, on the smoothness of this function f and g that comes up from the Pontriaggi minimum principle. Okay, which involves Lipschitz function. But the overall idea is that training and retraining real time for, closed loop control of different kind of application. We also did, and I'm not going to go too much into the details here. We're in the process of publishing this, but we also come up with the estimates of the generalization coming from the application of XTFC, both for the initial value problem and for the 2-point boundary value problem. As you will see here, the error generalized, we can bound the generalization error by controlling basically the quadrature error here that you have and the training error. Okay, and as you see, everything depends on the Lipschitz constant here coming up, for the two function f and g, and of course it depends on the time horizon associated to that. Okay. All right, let me give you some example, and then we'll move on to the stiff ODEs and the application of XTFC to stiff ODEs. For example, one of the problem that we tackled here is one typical problem that is important for space travel. Okay, we want to, for example, find the controller that optimally raise the orbit, go from example low Earth orbit to geostationary orbits. Okay, and we solve this in a planar problem. We just want to minimize the time to go from one orbit to an orbit, and the problem is standardly formulated. You have an ODEs, which is nonlinears, and then you have initial condition and final condition, and we apply the machinery. We do Pontryagin minimum principle, and you come up for this specific case basically with the state echo state, which is 6th order ODEs. Nonlinear, you have a transversality condition, which is another nonlinear condition that needs to be built up that enable you to find actually what is the final time, which is the minimum one, but is built up in the eventually loss function. And the way we do it, of course, we develop the so-called constrained expression. Here is it's kind of the the machinery here. And the idea is to find these C's parameters, which are the outputs of the weights of the free function that is introduced through the constraint expression. You build the loss, and then you go through iterative least square. By the way, we published these results in the journal Spacecraft and Rockets. It just came out a few months ago. So if you're interested in looking at all the details in terms of how we derive these, you can look at it. Once you have the loss, of course, you build the Jacobians, right? And then you go through the iterative least square kind of approach. This kind of the performance that shows how real time is possible, right? For example, in this specific case, you see the number of both points and training points in the field and in the domain, and the loss functions. You see the CPU time and the number of iterations that we converge it. Interesting part is that we compared this solution with the direct transcription through pseudospectral methods. There is a known software called GPOPs that implements that. And you see that in terms of, we believe we're more accurate, because our loss function is really smaller than what they get. But, you're talking about, 30 seconds, solution for this problem with the pseudospectral methods. And just for your reference, just give you, in this specific case, in this specific case, we went, for example, from Earth to the Sun. From Earth to Mars, and this is the trajectory that comes up. This is the direction of the control and the thrust as a function of time. Okay. All right. So we have other problems. Actually, Andrea D'Ambrosio here developed this idea of constrained optimal control problem using both PIN and TFC. Our approach here is somewhat transform the constrained optimal control problem into an unconstrained one and go through the machinery. Just to give you some of the ideas here, we applied these two problems where you want to go, for example, from two orbits. Two specific orbits near the moon. One, they're called Halo orbits. Their orbits, one is in front of the moon on the L1 point, the other one is behind the moon, which is in the L2 points. Are extremely important, especially now that there's a new race to the moon. both from government and commercial. So it's extremely important to come up with methods that enable you guidance and control of these objects. I'm going fast on this because I just want to show you that it's possible. And this is another example that Andrea put together here is Earth-Mars orbit, but now instead of doing minimum time, we do a fuel optimal solution. Now those are tough problems because fuel optimal solution means that the problem is in the controller. Basically the cost function is in L1, and is a known fact that you need a bank discontinuous solution for the control. This is the truss that comes out. You see, it has different switching function. In this case, from an accuracy point of view, it's much more complicated because requires basically a continuation procedure to capture accurately the switching, and the discontinuity. Nevertheless, it is possible. We apply the smoothing method and then eventually, a continuation procedure to get to the limit. Okay, this is a little bit less suitable for optimal control because they're more computationally intensive, but nevertheless possible. I think I'm running out of time here. I just want to, I don't want to, take some time on the stiff equation. Just want to quickly mention also that, we have tried to apply XTFC by solving linear optimal control problem with finite time, where you basically the necessary and sufficient condition yield the need to solve the so-called matrix differential Riccati equation, and this is the formula. Given a linear system and a quadratic cost function, basically you end up with this matrix differential equation of the second order because P and P shows up here. It's a final time kind of problem. So if you find P, then you have a closed loop solution. And the highlight of this is that basically, those equations are relatively hard to solve, especially for real-time applications, because they tend to be numerically intensive and stable. Of course, if A, which is the matrix, depends on it's constant, you can solve it offline once per all, and it's fine. But if it's time changing or it depends on your operating points, and things are different, you might need to solve it online. The problem is that when you get situation like this, and you want to try to apply, for example, direct integration, right? Transforming the matrix problem in a system of ODEs, turns out that the problem tend to be fairly stiff, and you need the very small time steps, which might not be suitable for real time. We applied, and Mario will talk a little bit more about what we call the domain decomposition, where we split the timeline in a basically smaller domain. We try to solve one at a time, marching forward or backward in time, in this case, for the matrix differential Riccati equation. And we apply this to a specific real problem where it has to do with the intercept between an interceptor and a target. This is extremely important because it solves what they call integrated guidance and control for an interceptor that outside the atmosphere try to capture or specifically hit an incoming threats. What we show that it turns out that because things change as you go in time, you have to solve this iteratively. I'm not going to go into the details of this, but basically you end up solving a 6 by 6 dynamical problem, which ends up being 6 by 6 matrix Riccati, differential Riccati equation. I just want to show you that we implemented the XTFC in a model predictive fashion with 1 second time horizon. In this specific case, we didn't use extreme learning machine. We use what we call the Chebyshev neural network with the 50 basis function. The important thing is that we were able to show that using our approach and using iterative least square, we're able to converge in 7 iterations for this specific problem and having a 0.9 second computational time with the norm of the error, but of the loss at least 10 to the minus 60, which is close to machine accuracy. Important thing is that we believe that these with the appropriate coding can be basically go down 1 or 2 order of magnitude, which means you can potentially recalculate this solution as you go for fast flying system with the frequency in a cycle comparable to what is currently implemented today for these systems. Okay, so
Roberto,
yeah.
before you go to the stiff kinetic, both the topics, by the way, are of interest to us because we have ongoing projects. But we have in the audience people who may want to ask a question here before we go on, and we'll give you extra time at the end.
Okay, but, I'm trying to be respectful of the time.
For example, let me ask Ting Wei Meng or Chen Chan if they are listening. Recently, we co-authored a paper on Hamilton-Jacobi and pins and symplectic integrators. And I was wondering if Ting Wei Meng has any questions. Or Jen.
Hi, Dr.
Jen. Jen.
Yeah. Hi, Dr. Furfaro. Thanks for this very wonderful talk. And I'm actually very interested in the part that how you handle the your constraints. So I see that, like in the previous slides, you have some like C times H. Like, could you just maybe elaborate a little bit more on that specific part? So is it like Lagrange multiplier that you are applying, or is something else?
Which one are you talking about specifically? Can you point me which
problem? Yeah, sure. Could you go to the previous
this one or the one above?
Like in the methodology part where you have some
in the beginning, I think. Yeah.
Okay. Yeah. So basically the way it works, so that maybe here.
Oh yeah.
But the way it works is basically the following. And this is the power. We are trying to merge both extreme learning machines, and theory of functional connection. So the power of theory of functional connection is the one that enable us to handle the constraints analytically, right, and satisfy them exactly. Okay. The way we do it is basically we describe your solution, which is what you're looking for, solution of an ODEs or the PDEs, as 2 parts, right? One is unconstrained, and the one is a free function. The other one is this other part, okay, where basically you satisfy automatically through this constrained expression the boundary conditions. Okay, now we can spend an hour explaining how this works, right? And that's why I'm kind of pointing out a little bit to the work of Dr. Mortari. Of course, my group now became very fluent and familiar with this one. But the way it is work is basically this part. The whole thing is called constraint expression. Constraint expression is such that basically by representing this y through a free function in something that automatically satisfies the constraints, basically what you need to do is to, depending on your constraint, this is kind of a general formulation, basically you express, you add up this term, right, where nk are coefficients to be found, and sk is called support functions, basically a basis function. There is some constraints there that you need to satisfy. For example, if you represent G, I don't know, and then an expansion of Chebyshev polynomial or any polynomial, you want to make sure that the support function are not in the space, are not linearly dependent of this function. You have to be care about this. But basically, once you choose the support function, you need to solve a system to find this eta k. And as I said, there is a systematic way of doing this. And once you do this, you automatically, analytically, I would say, satisfy the boundary condition. So now you have to solve an unconstrained problem, okay? Where you find only, for example, either the beta, or if you use a deep network, you find only, the weights, solving an unconstrained optimization problem. So the boundary conditions are automatically satisfied, okay? And that's what we did, for example, here for our application. Now, the application, we try to explain here when we solve two-point boundary value problem. The first thing that we do is develop this constraint expression, right? Where we have this free function, find these constraints, put them into the two-point boundary value problem. Then, for the unconstrained problem, solve the loss function. So build the loss function and then solve for the weights. I just want to point out, for example, here, as you see, right, this is basically the steps, and it's really hard to see it now. That's what I'm saying. You have to kind of look at either at this paper, or we can talk offline too. If you guys can contact me, I can give you a little bit more details. How you go about building this constraint expression, okay, and then build the loss out of the unconstrained results.
Okay.
Yeah, sure. Yeah, thanks. That makes sense. And
maybe Zogren, you can put on the chat our paper for Roberto and his associates to see that we're using also symplectic integration, using your symplectic Hamiltonian system. So I think they may be interested in that.
Yes,
we had a talk here on extreme machine learning some time ago by Steve Dong from Purdue. I don't know if you have seen this, their work also. They get pretty good accuracy in some, not for control problems, for standard PDs. Steve was my postdoc for a long time, but he presents some impressive results. So I know they have at least 2 or 3 papers on extreme learning machines.
It would be good to exchange notes and look at it. Enrico did quite a bit of work in applying this to also PDEs, right? If you look at the publication that we had on neural computing, where we presented for the first time.
Yeah, so forwarded. Yeah, I saw that. Yeah.
We also took a serious look about comparing what we call deep TFC versus XTFC. The difference between the two is that TFC always is employed to analytically satisfy the boundary conditions, right?
Yeah.
And the initial condition, but then we compare deep TFC versus XTFC. Again, it's a trade-off between accuracy and time. Certain problems, certain PDs, for example, Navier dogs, right? When the nonlinearity goes up, many times what happens is, it's problem dependent. Deep TFC might be better suited, right? But XTFC tends to be fast. Depends on the level of accuracy, again, that you need. From our control application, fast is better than super accurate. Let's put it that way. So we're trying to strike balance.
So on that note, I don't know if you're familiar with the DepotNet that we have developed, which is only trained offline, and so for all real-time applications, including hypersonics. Actually, we had the DARPA project. DepotNet is our preferred choice. So that's another aspect that you may guys want, with your knowledge, you can incorporate in this.
Yes. We're looking, at it. It's and we're trying to progress as much as we can, right?
In fact, we have DepotNet here. Meja is using the DepotNet for stiff ODEs for detonations. The next subject, but maybe we can talk after the remaining of the presentation. Yeah.
I had a quick question. This is Michael from Utah.
Yes, Mike.
I was just wondering, I guess, if you've tried this, or what your thoughts are on using things like RNNs or LSTMs, since it seems like a more natural way to do optimization, as you get the input from the last state. For example, the Hohmann transfer that you showed, it would keep the state of the last position of the spacecraft, instead of having to go off of measuring gravity, integrating that to get your state vector. It might help the network, or I don't know if you've tried this, or what your thoughts are on that, if that makes more sense than a fully connected network for these problems for control.
Yes. Thank you for the question. Usually what happens is when you try to solve this kind of problem, you're looking for eventually, although if you solve the Hamilton-Jacobi-Bellman equation, you're solving a closed loop. You're solving basically the sufficient and necessary condition for optimality. So you find U as a function of X, which is the current state. Okay. Now, in optimal control theory, which comes from a deterministic kind of approach, it doesn't account for previous, states. The dependency is captured through the dynamics, right? When you implement recurrent networks, then somehow you're kind of keeping track of the memories, keeping to memories what happens, before. To capture dynamical system, it is good, in general. But for recurrent network, for solving closed loop optimal control, I'm not 100%. I mean, again, it could be a possibility, but it doesn't seem to be relevant because, the solution of the ODEs should give you, approximately this is it's important because you capture all that locally, so to speak, and globally. Now, however, I have to say something. There is another parallel path that my group is taking, which is using reinforcement learning, okay, and reinforcement meta learning. There, however, we are using basically deep recurrent neural network to capture, however, or keep in memory the fact that there are uncertainty into the systems. So that helps, okay? My sense is that it might help less in deterministic kind of problems like we are approaching now, okay? But the recurrent might help if you account for uncertainties, right? Because the system in a meta-learning framework can keep in memory what's happening in different kind of scenarios, slightly different scenarios.
Okay, yeah.
That is my take on. That is my take on, but it might not be absolute, right? So people should try. It's just coming from an optical control theory. Usually, people synthesize controller as a function of the current state. It's kind of a little bit Markovian, if you think stochastically, but in that framework, Markovian theory doesn't exist because it's deterministic, so to speak, right? So.
Yep. Thanks, and it was a very good talk.
Yes.
Hello, this is Lulu from UPenn. I have also one question here. So for the TFC, so I was wondering so in which case can we apply TFC? For example, if we only have, in your case, you have 2 points in the middle, then left and the right point should be equal. So actually we also applied a lot of this kind of hard constraints to the pins in order to satisfy automatically the boundary or initial condition. So, but if we consider, let's say, if we have a triangle domain, in one boundary of the triangle, we have Differential boundary condition. In another one, we have Robin. Another one, we have some period, maybe some other types. That can we do it or?
Yes. The answer is yes. General is very general, and you can. How you do it is kind of a little bit different story, and that's why this TFC, so to speak, book came about. Many articles from both our group and Dr. Mortari's group that can show how can be done. So my suggestion is, I have a feeling, and this is again a little bit. Again, I come more again from an applied, engineering kind of position perspective, right? But I feel like that some people in the community, more in maybe the applied math community, thought that the TFC tried to solve a problem that is already kind of being looked at, right? And I was thinking about, for example, the Lagarde's paper, right? The one that 2002 started doing the neural network, application to PDEs, right? That was before even the wave of deep networks or even the physics informed, right? But if you look what they did, right? They tried to do something similar that they tried to satisfy the boundary condition first, and then try to, use the neural network to represent the other part. So what's the difference with TFC? Is that they had to do ad hoc problem. They have to go look at the problem and find out the suitable function, right? That satisfy the boundary conditions. Here, the TFC enables you to do this systematically. It's kind of like almost an automatic machine once you understand it and you implement it, and it is kind of automatically done. There are prescriptions how you do, and it is done for all sort of problems, for all mixed boundary condition that you want, for integral condition, for multi-points, as a matter of fact. Okay, and in some case we use, for example, if if we know where is the discontinuity on the problem, we can split the domain in different parts and use the TFC to automatically satisfy the condition, for example, discontinuity or what have you in the points of interest.
Okay, I see. Thank you. So, by the way, so what's the limitation of TFC? I assume this method should have some limitations, or
yeah, of course.
some clearly cannot handle.
For example, again, it's for the problem that we looked at, right? We're able to capture the boundary condition. Of course, application to general domains like finite elements methods, it's harder, right? But there's been some work done and tried to generalize to any possible shapes, right? And I think there's been some success and some not, right? The other things that recently, for example, we realize it cannot be applied is when you work in that you needed some extension. And eventually, Professor Mortari realized that it's possible. Is, for example, when you have a structural mechanical problem, right? And you have, the equations, the conservation equations and what have you. Many times, they realize that, for example, some of the boundary conditions were on the mixed derivatives, right?
Yes.
Like, for example, right, because you have to represent the stress, the boundaries. And for example, talking to him, we realized that was not contemplated by the theory. So he had to do a little bit of an extension of how you do it, and is in the process of being published. How you do it to work on this. Another things that we're doing, the two of us, for example, is looking at fractional derivative, fractional ODEs, and fractional condition. I think it can be extended, right? So I wouldn't say, as I said, it's kind of work in progress in the sense, like for the problem that we saw, it seems to work and seems to be very general, but every time comes something that maybe we don't know how to do it and needs to be extended a little bit more. Okay, but I would say that the big, however, generalization is a big deal. Okay.
Yeah. By the way, and thanks. You see, there's great interest, Roberto, from everybody here. We have fractional pins in case you dive into fractional, because we are a fractional shop in my. For the last 6 years, we had the Muri, so we did a lot of stuff. But maybe we should proceed with the remaining of the talk, and Enrico can take more time. Yeah.
Yes.
But there's a great interest in your talk.
Yeah, thank you for the question. I didn't try to rush it. I was trying to be a little bit cautious for time.
So Zogren, we will continue the same talk, just the second part of the talk, okay? Yeah, this one here. Yeah.
Which I believe you'll be very interested. Mario, are you on?
Yes, thank you, Roberto. In this part, I will be brief. In this part, I'm going to talk about how we can apply XTFC to solve stiff problems, in particular with application on stiff chemical kinetics. And because as we know, stiff problems can be very tough to solve with the traditional numerical methods, mostly because of the steep changes of the solution, and in particular for large time or space domains. Next slide, please. So the main idea, which is pretty simple idea, is to decompose the domain in equally spaced subdomains. What we want to solve here is are stiff systems of nonlinear differential equations. The main idea is use XTFC, the framework, as Roberto explained before, by using the constraint expression, firstly for the first subdomain. And we can do it directly with the XTFC without any modification. Then we apply for each interface of subdomains a condition for continuity, which means that the final solution that we find at the right side of a subdomains will become the new initial condition for the next subdomains. So basically, we can apply XTFC iteratively until we find the solution at the final part of the time domain. Of course, these are initial value problems, so that's why we can apply this kind of algorithms. Otherwise, for 2 points boundary value problem will be a little bit different. So we applied for stiff chemical kinetics, and I'm going to show you 4 of the problems that we solve. Roberto, next slide, please. Basically, how it works, we want to find the unknown function y as a function of t. We approximated with a constraint expression from the theory of functional connection. And the free chosen function will be a single layer neural network that will be trained via extreme learning machine. And thanks to the constraint expression, the initial condition will be always analytically satisfied. So since we used an extreme learning machine, the only unknown outputs, the only unknown parameters are the output weights of the neural network. So once we build this constraint expression, we're going to replace them back into our stiff systems in our system of nonlinear differential equation. And we want to minimize this lossless function that we find to find the optimal output weights of the neural network and replace them back into our constraint expression. We can find our solution. This scheme that you see here in these slides works for the first subdomain, and then again, iteratively, you will apply it for the next ones. Next slide, please. So the first problem that we solve is the Robertson's problem, also known as a Robert problem, which is modeled by 3 differential equations, nonlinear differential equations. So according to the literature, we wanted to solve this problem for a very large time domain, up to 10 up to 5 seconds. So in this case, we didn't need very small time steps, but we used pretty much wide ones, like 20,000 seconds per subdomain. And according to other methods in literature, our numerical solution can be compared with those solutions up to the 12th digit of accuracy. And on the right side of the slide, we can see our comparison with XTFC comparison with MATLAB function to solve a stiff problem called ODE 15S. And the absolute error between our solution is of the order of 10 up to -15 to 10 up to -5. Next slide, please. The second problem is called the chemical axon novel, and a little bit more complicated than the previous one, since we are dealing with 6 nonlinear differential equation. And here the time domain is much smaller, but still we need a domain decomposition, and we employed a 0.01 seconds of width of subdomains. And we can see the comparison with the XTFC solution again against the ODE 15S, which we can see that XTFC is pretty much accurate, but much slower than the MATLAB function. We can see 6 seconds against the 0.02 seconds. Next slide, please. The third problem is called Belousov-Zhabotinsky reaction, and it's modeled by 7 nonlinear differential equations. I found this problem in many papers in the literature, and all of them were solving this problem for 40 seconds, which is pretty small. So I tried to solve it with the XTFC and the ODE 15S, and we can see that, for example, XTFC, the blue line, can find for 40 seconds 3 steep changes for all the 7 concentration of the reaction. And we can see that the ODE 15S, which is the red dot line, will fail after the first steep, after the first jump, if we can call it like that. So we used as another comparison of the ODE 15 which will be made for more complicated, more complex stiff problems. And we can see that the ODE 59 can get all the three steep changes, but with a little delay of compared with the XTFC solution. So our doubt was how can we see who actually is more accurate between the two of them. So next slide, please. So what we did, it was extending the domain, the time domain up to 120 seconds. And we could see that actually ODE 59 was failing to find the solution after the third jump, while XTFC was continuing to find the same trend in the steep changes along the domain. Here, for both 40 seconds and 120 seconds, we needed less subdomains. We can see here we needed 0.01 seconds per each subdomain, while the MATLAB functions needed 0.0001 seconds. Still, XTFC is a little bit slower, but at least doesn't fail in finding the solution. So our doubt now was how much we can push XTFC to solve this kind of problems, because these are real-world problems for much wider time domains. So next slide, please. So we extended, in the right plot, we can see that we extended up to 5,000 seconds. And by zooming on the solutions, we can see that XTFC still is finding all the jumps which we can think that is pretty much accurate. Again, even here with the 0.01 seconds time steps, and for this case it was 400 seconds of computational times. Next slide, please. The last problem that we want to
Mario, what's the time step for the ODE solver? I know it's an adaptive solver, but approximately what's the time step for the ODE solvers?
You mean MATLAB function solvers?
Yeah.
0.0001.
Oh.
So they needed much more.
Okay. Oh, yeah. I see. You have it on the table. Yes. Thank you.
Yeah. So the last problem that we want to solve is a real world problem, is a pollution air problem known as a POLU problem, that is made by 20 differential equations, nonlinear differential equations. Next slide, please. We would be very fast here. Just to show how, again, the next one, here is just the chemical reaction with the reaction rate and constants. And again, here we compare it with the ODE 15S, where we can see we can compare our solution with ODE 15S, seeing our absolute error between the two methods in the order of around 10 up to minus 13, I would say, sometimes minus 10, minus 15. So pretty much good accordance with the agreement with the MATLAB functions. And this actually is not the first time that we applied this kind of framework, because the first time it was the first paper that we published with this algorithm was to solve a point kinetics equation for nuclear reactor dynamics, which we found great accuracy according to dozens of papers published in the literature. So I will say we're done with the stiff problems now. Next slide.
Okay. All right. I put a little bit conclusions, just just to remind you that our group pay attention or is going toward real-time implementation. So we're always try to find approaches that use spin and they can be fast and accurate, right? And of course, along the way, we we're trying to solve XTFC. We try to apply XTFC to problems that require high accuracy, right? We try to, for example, as Mario mentioned, we looked at some nuclear reactor or kinetics. We're in touch with the community that does benchmark, solution also, for example, for ratified gas dynamic equation that requires solution of integral differential equation. Recently, we published some paper there. Just before opening also for more discussion, time pending, I just put here some of the recent journal papers that we put together, and some of the conference or preprints or things like that. Okay. All right. I think we're done here.
Thank you, Mario. Actually,
Thank you, George.
The Robert problem and the Polu problem that you showed. We have Ameya here, who is assistant professor in research in my group, and I'm sure he has solved this many times in different ways with DepotNet, and because of this detonation problem I mentioned. Your results are impressive in terms of accuracy. Ameya, do you have comments for Mario? I thought it was a great results, but do you have any comments? We could do a direct comparison of the couple of methods. Have you published this work, Roberto? Which paper is this on that Mario showed us?
Oh, it's the cows one.
Was it cows and the cows? Yeah, okay.
Yeah.
Actually, that's why I think I contacted you. Yeah, because of our interest in that. Yeah, okay.
That's the cows. That's why I brought Mario into, because he's the one that directly worked on this. But we're more than happy to work with you, compare and see, and try to see what's the story.
Yeah. So we have also the DepotNet, which we can go from the initial condition to the final in one shot. And of course, that doesn't cost you anything, but the hidden cost is, of course, at the pre-training. And so
at the pre-training, yeah, I got you.
If you, like in what these people are trying to do is, and these are real world applications. It's an STTR that we have. It's they don't want to change the hydrodynamic codes. They basically want to train the chemistry, and the disparity in time steps will be 8 orders of magnitude. You show 4, but actually, for these other problems, which have 300 equations and so on, there's a disparity of 100. So you sort of have to learn, because you will be calling this, we call DepotNet, for example. So we do all the pre-training. So it's really interesting, but I'm impressed with the accuracy of the method, because when Steve Dong from Purdue came here to give a talk, I was sort of questioning the extreme learning machines, because first of all, I said we shouldn't be calling it learning. According to information bottleneck theory, if you look at how the neural network learns, it fits the data in the first few layers, and then it learns for the rest of the layers. In other words, that's why I want to study your generalization error, because I don't believe that these extreme learning machines, which are very accurate, I don't believe that they can generalize.
It is. So let me tell you a little bit my take on this, right? A little bit of history. It was 2012, right? I was chairing one of those IEEE World Computation Intelligence in Australia, and I think I came the day before, so I had kind of a morning, and there was this tutorial sessions, and there was one being who was giving this 4 hours, tutorial on extreme learning machines, and the name sounded intriguing, and I sat down and he went through this, and I was almost didn't believe him, right? Because it seemed to be, he was calling it tuning without generally without with iteration, things like that. Now, my sense is that he might have oversold that, because he also claims, right, that he generalized the best, right? He has the best level of generalization, because he tends, at the time I was talking about shallow network only, then people start working toward maybe doing, the random, deep kind of networks, features into. But he was claiming at the time that it was giving the minimum weights anyway, right? Possible. And so I was a little bit skeptical. I pursue it simply because of the fast and accuracy, right? But again, I think it's also problem dependent. I don't believe that it's the solution for everything, right? So
also, I don't think you can show convergence.
Yeah, that's a thing that I'm actually currently looking at
With a number of bases, because you cannot have completeness, and but right. it works. I've seen from the papers of Steve that I studied recently that he's very careful on how he's selecting the distribution. So he doesn't dare to do a new problem unless he knows the answer. But the accuracy is impressive. I mean, I have to give it to that, because the problem that he solved very accurately, something that the pins would not do it. It's just but you demonstrated that also very good accuracy. I'm impressed with the accuracy that Mario showed. So so we will look into the paper, and maybe we can contact you to follow up with Mario.
You might want to look also, because see, one of the things that we did, there are certain problems that we're interested in benchmarking, right? For example, there is the first when Mario came to my group, one of the first things that we tried to do is because I had experience personally in solving integral differential equation coming from radiative transfer, right? In that case, you have a solution where the integral part depends on an angle and it's discretized through integration. So you end up solving a system of ODEs, right? Large, depending on your, and we were able to do benchmark with that problem that in the community, in the transport, what they call the transport community, is considered extremely challenging. And we already knew that, this kind of methods might get, very impressive in terms of, accuracy. We try also ratified gas dynamics, which is very similar, integral differential equation. So somewhat the results to us when Mario started applying to this, to us somewhat were not surprised, simply because we saw in other challenging benchmark level domain that we could get that kind of accuracy.
Yeah.
But I think we need to understand a little bit better, a little bit better, but what makes this so accurate, right? So
it's interesting. It's interesting to be a topic to be analyzed. Any other questions for Mario or Roberto before we proceed to the next talk?
Hi, Doctor. Excuse me. Hi, Dr. Furfaro. This is Jen. I have another set of just two questions regarding your first talk. And first of all, it's I think you mentioned about the cursive dimensionality at somewhere. So I'm curious about what's the highest dimension of problem that you are considering in your paper. And the second question is, in the case when when the dimension of the problem is high, or you are considering complicated dynamics, it's hard to get a baseline for a model. Then how would you evaluate the performance of your method in that, if that is the case?
Okay, for the second, you might need to repeat, but let me answer. Let me answer the first question. Okay, now, so let me tell you upfront that we're also looking at solving the Hamilton-Jacobi-Bellman equation for control. Okay, but I haven't presented here because I think for us priority now is to solve this, 2-point boundary value problem. Now, the 2-point boundary value problems that come up from Pontriaggi minimum principle are one-dimensional, right? So in this case, they're relatively, the lowest dimension you can go. So it's a 2-point boundary value problem. It's not a PD. Okay. However, the challenge there is that you close the loop, by solving this in real time in iteration way. Now, the other approach is to go to the Hamilton-Jacobi-Bellman equation, right? There, of course, we started solving highly nonlinear but two-dimensional problems with XTFC, and it seems to work very nicely. I didn't report the results here, okay? But for practical problem, we had, for example, we're putting together a paper where we're doing attitude control, closed loop attitude control for the spacecraft. And in the axial symmetric case, it simply end up being a 4-dimensional problem. Okay, so I think in solving PDEs, we went up to 4-dimension. Okay, for control applications. Okay.
Yeah.
Roberto, Jen, this is a paper that they Jen that Jerome Darpon who so they have 256 drones in a room that can cross from one place to the other without hitting it. So they're basically in 500 dimensions.
Yeah, that's huge. Yeah, that's really huge. Yeah, but we haven't.
So you can see now, as the movie is playing, they move from one to the other. They don't hit each other, and so of course they go across to the other wall at the fastest time. And this was done on a GPU in 1.5 hours on a single GPU.
Awesome.
Yeah. So this is in that paper that I gave you. So we're sort of targeting high dimension. That's where this question from Jen comes in. Jen, maybe we have to.
It's really good, but we never tried to go higher. Simply, as I said, we're starting more from a model predictive control point of view. We're kind of extending now and I'm interested in the specific applications, right? But anyway, this is something we need to look at it. It's really, really, really good. Actually, can do this kind of things with this approach. Okay.
Thank you again, Zogren. You may want to introduce Varun, who is impatiently sorry for the delay, but here we freelance group. We ask questions.
Thank you. Unfortunately, I got to check off. I have other meetings, but I appreciate invitation. I hope you find it interesting, and we'll be in touch. Okay.
Sure. Thanks.
Thank you.
Okay, so let's move to our second talk. Our second speaker is Varun Shankar, who is assistant professor in the School of Computing at the University of Utah. He's also the associate director of the Master of Software Development program. His primary research is in high-order meshless numerical methods and more broadly in the field of scientific computing. More recently, his interests have grown to encompass physics-informed and scientific machine learning. He obtained his PhD from the same department's School of Computing in 2014 and was a postdoc in the Department of Mathematics from 2014 to 2018. So without further ado, let's welcome our second speaker. Sorry for the delay, but you may want to start sharing screen.
Sounds good. Oh. Can you see my screen?
Yes.
And my audio is okay also?
Yeah.
All right, well, thank you all for having me over. I'm excited to give this talk. This is my first PINS talk, so be gentle. So the title says that this, I'm going to talk about accelerated training of PINS using meshless discretizations. So just a sort of little background on this project. My collaborator, Ram Sharma, who's also actually here in the Zoom speaker list, I think he has his video on. He was an undergrad at my alma mater, SRM, Institute of Science and Technology. And we both started working together, and we were exploring, what kind of projects we could do. He was a machine learning guy, I was a scientific computing guy. And so we said, okay, I sort of said, let's look at PINS. And we had some kind of loss function, which we couldn't differentiate using AutoCAD because it was just scattered samples. And so we said, oh, let's use discrete differentiation. And this sort of idea of using a meshless discretization is one. That's sort of the high level picture. I will dive into all the details, I promise. This work was funded by NSF. Okay, so I'm going to use the nonlinear Poisson problem as my prototypical problem. And then we'll drop a term and do the linear Poisson. We'll also do heat. The PDEs in this talk are really, really simple, maybe even simplistic. But the goal was to pick examples that help us tease out the strengths and weaknesses of our method. So this is pretty straightforward. This is the nonlinear Poisson equation. It's nonlinear in the sense that there is an e to the u term, where u is the solution. We're dealing with sort of general boundary conditions. So we have Robin boundary conditions, and alpha ddn plus beta, think of that as the boundary condition operator, which I'm going to refer to with script b. And n here is the unit outward normal to the domain omega, whose boundary is d omega. Right, so let's assume omega is curved, or d omega is curved, so that this doesn't map nicely to a regular Cartesian grid. Alpha and beta in general could be functions, of course, but in this talk, they'll just be like numbers. I'll always just pick them to be 1. Oh, and g of x and f of x are specified. So you all know this stuff already, but I'm just going to use this slide to establish notation. Okay, so let's say we have some set of collocation points, and I should mention we're working with the unsupervised version here of pins. And so I'm not going to distinguish between collocation points and any other sort of supervised data locations or anything. We're just going to call them all collocation points. It's only one set of points in the domain. So let's say we have some set of collocation points, and there's n of those. Let's call that set x, right? We're going to divide this up into 2 sets, interior points and boundary points. Okay, and we're going to refer to those sets as xi and xv. There's ni interior points, nb boundary points. And let's say u tilde. So whenever you say tilde somewhere in the start, it's an approximate quantity, not the actual quantity. And so let's say u tilde, which is a function of x, and the vector w is some deep neural network. And the vector w is its weights, the weights of this network. Right. So as you all know, the goal of this, if you're trying to develop vanilla pins or pins as a solver, I'm going to call them vanilla pins for the rest of the talk. The goal is to find W such that we approximate the PDE solution, such that we approximate U to some desired tolerance in some norm that we want, right? So let's say epsilon is that tolerance. Maybe this is L2, H1, whatever you care about. Right, so for traditional, at least for the original pins, which I'm calling vanilla pins, this means that you enforce the PDE and the boundary condition as typically soft constraints on the DNN. Right, so let's move this annoying Zoom thing away. Yeah, so it's pretty simple, right? Now that we've divided our collocation nodes into a set of interior and boundary points, all we need to do is enforce the PDE loss at the interior points, which is the first term you see here, and the boundary condition loss at the boundary points. Right, and we're doing here in this mean squared error sense, so I imagine you could do it in other ways also. This error is a function of both space and the weight vector W. And so now you want to optimize and minimize this error, find the W until you achieve some tolerance. Hopefully then that DNN is a solution for the PDE, or you could think of it as a proxy for the PDE solution. Now in traditional frameworks, so sort of thinking of not what we're doing today, but in general what people do is both spatial derivatives and derivatives with respect to the weights are computed using automatic differentiation, which I will just call autograd for the rest of the talk, because automatic differentiation is a mouthful. And typically, from what I've seen in the pin literature, one uses 32-bit floating point, FP32. Now, this is absolutely the most basic type of pin, right? This is many years old at this point. But I want to focus on this version. I'll mention that there's other variants that one could talk about, right? Variants where you add a supervised term to the loss, G pins, where you add gradients, where you penalize gradients, X pins, C pins, and even learnable activation functions like the stuff you guys have been doing recently. But I want to focus on this very simple setup for intuition and clarity. And then hopefully all the stuff we talk about will carry over to these other kinds of pins also, or these other settings also. So I just want to sort of list what I think are the pluses and minuses here. And we'll see what we can do to fix the minuses. So basically with vanilla pins, once the vanilla pin is trained, the solution can be evaluated anywhere within the domain. And because you're using autograd, you can handle almost any differential operator, except fractional ones maybe. In those cases, what I've seen is people use numerical differentiation instead. And the fact that you're using autograd plus some sort of over-parameterized DNN allows for a properly meshless method, where you don't actually need a mesh to find the solution to the PDE. You can just solve PDEs directly on point clouds. What's really cool, in my opinion, the coolest thing about pins is that all these operations map cleanly onto traditional ML pipelines, which means you sort of get GPU parallelization for free. And you can use the GPU parallelization built into ML pipelines, built into popular libraries, and just sort of use that. The one small issue that we've seen is that training can be slow. say compared to traditional numerical solvers, these could take a while unless you have some heavy duty hardware. And this is the thing that actually motivated this work. Most existing AutoCAD implementations, at least in most of the popular libraries, are horribly slow. I'll come back to Jackson by the end of the talk, but most of the mainstream ones are horribly slow for higher order derivatives. And so training becomes slower for higher order PDEs. There is this idea of Taylor mode differentiation, which actually overcomes this limitation. I will readdress that at the end of this talk. For now, let's focus on, let's think of it as PyTorch's AutoCAD, or whatever AutoCAD that's not in Taylor mode, but traditional sort of graph navigating sort of things. Okay, so the idea is to use discrete training, and I'll explain what that means. We're going to try and keep the plus points on this slide. So we want to be able to handle arbitrary domains. We want to be able to solve PDEs and point clouds. We want to map to traditional ML pipelines, but we don't want training to be slow, and we don't want higher order derivatives to be slower to compute. Right? This is the goal here. And so if you want to be able to handle point clouds, and you're going to use a discrete differentiation operator, we need some sort of meshless numerical method. If you care at all about accuracy, I'm going to show that you need a high order method, a high order numerical method, plus FP64, 64-bit floating point to maintain accuracy. We want to formulate everything so that we can still benefit from GPU parallelization and all the traditional ML good stuff. And finally, none of this is worth it if our training is not faster. Right? There's no point in replacing AutoCAD and then ending up with some method that trains slow. Okay, so these are the goals I'm setting out for the talk. The outline of the rest of the talk is as follows. I'm going to talk about radial basis function generated finite difference methods. This is called RBFFT. So in there, I'm going to review classical FP methods and then talk about how one gets to modern RBFFT methods from those classical FD methods. I'm also going to talk about a variation of RBFFT that I developed, which I called overlapped RBFFT. The one could probably come up with a better name. And this overlapped RBFFT allows for massively faster assembly of these differentiation matrices in serial, even without parallelizing. Okay, so we'll talk about that. Then I'm going to talk about what we call discretely trained pins, DT pins, and we're going to use overlapped RBFFT for these discretely trained pins. The idea is very simple. So I'm going to spend a lot of time on the RBFFT part, and then most of my time discussing the results. The one issue that we did run into is that we needed to write custom AutoCAD functions. I want to spend like a couple of slides talking about that. In the results, we'll compare AutoCAD and RBFFT. We'll do a linear Poisson problem where I just drop the e to the u term. We'll do the same nonlinear Poisson problem that is on the slide. And we'll do mixed training for the heat equation where we use AutoCAD in time and RBFFT in space. If you have questions at any point, feel free to interrupt. Okay, so this is going to be annoying because everyone knows finite differences, but there's a reason. I sort of want to present notation and discuss finite differences in a certain way that motivates RBFFT. So recall that finite differences actually approximate derivatives at some point, let's say x1 here, and f some function, and you want some derivatives, or in general, any linear operator applied to that function f, and you want to approximate that using a weighted linear combination of function values, right? And those weights are called FD weights, or finite difference weights. In one dimension, or technically even in 2 or 3 dimensions or whatever, they can be generated in at least 2 ways. Right? The first approach is to use Taylor series, or if you're feeling ambitious, you could try and use a limit definition of the derivative recursively. The second approach is actually to use polynomial interpolation. Now, the cool thing is that both approaches give the same finite difference weights as long as you're using polynomial interpolation and not least squares or something. So I'm going to discuss the second approach, meaning the interpolation approach to generating finite difference weights, because that's key to understanding RBFFT. So let's say f is some function, and we want to approximate its derivatives, and script L, mathcal L, whatever, is the linear operator for which we want finite difference weights at some point x star. Here's a possible way to proceed if you were to use polynomial interpolation. First, you could sort of write down some polynomial expansion. Again, this is all just sort of illustrative. You shouldn't use monomials. You should never form a Vandermonde matrix unless unless there's no way you can avoid it, right? But let's just talk about it, at least in theory. So you can form some sort of monomial expansion and enforce interpolation conditions and find the coefficients alpha that ensure that your polynomial interpolates the function f, right? We can write this all in vector form. So P you can think of as the Vandermonde matrix, alpha as the vector of coefficients, y as the data vector. And so at least in theory, alpha equals P inverse y. Never invert a Vandermonde matrix. It's a bad idea, but I'm just saying, at least in theory, this is true. Once you found the coefficients, you can now differentiate that polynomial interpolant to get the derivative, right? So let's say B, the matrix B, contains derivatives of the basis functions. So L, the script L applied to the monomials, whatever script L is, any linear operator. And then now you can see that to find the derivative of the polynomial at the point x star, which one hopes approximates the derivative of the true function, you can write that as B times alpha. But note that alpha is P inverse y. And so you get B, P inverse y, right? If you combine B and P inverse together, that actually gives you L, the finite difference weights for approximating script L. In other words, if you look at this process, somewhere in there, the finite difference weights have sort of popped out. Looking at this, you realize that since L is BP inverse, if all we wanted was the finite difference weights, which only depend on the positions and not the data, we could just directly solve for them by solving P transpose L transpose equals P transpose. What that system looks like is this, right? This is the transpose of the Vandermonde matrix. This is the weight vector, and this is L applied to the monomials. This is if you're using monomials, which you should not. I'm just pointing out. Of course, if you look at something like this, there are fast algorithms to do this using divided differences or the Lagrange form or the barycentric Lagrange form. Bengt Fonberg has a couple of papers on generating finite difference weights in arbitrary dimensions for arbitrary differential algorithms. But what's relevant to us is that if you use every point available to you, all the data points, then L is a dense matrix, right? Here it's just a vector, but in general, L is a dense matrix, and this gives you the differentiation, pseudo-spectral differentiation matrices from classic spectral methods, right? If you, however, use small neighborhoods, which are typically called stencils, then each L is actually a row in a large sparse matrix. This is a classic finite difference method. The problem is, once you go to any dimension higher than 1, polynomial interpolation needs either tensor product grids or simplicial meshes, or you need to sacrifice, sort of relax the interpolation constraint and go to least squares, right? To keep our method meshless, we're going to use radial basis functions, and we're going to still interpolate, and we're going to set up things in such a way that we can reproduce polynomial derivatives exactly. This idea leads us to radial basis function finite differences. You can generate finite differences using RBFs on scattered nodes with polynomial-like recovery properties. You can do it on surfaces without using any metric tensors. And you can use local RBFs in conjunctions with local polynomials on stencils to get highly accurate, high-order finite difference formulas. There are certain proofs of optimal recovery if the target function is in the right Sobolev space. So even if it's not, the target function is not polynomial, you get certain guarantees of recovery. And finally, of course, you can build in polynomial reproduction so that the weights are exact for polynomials up to some degree. Okay, so here's a picture, right? So let's say there's two nodes here. There's the red one and the green one. And there's a bunch of neighbors that they have. So you pick some finite number of neighbors and you call that a stencil. You could select these neighbors using a KD tree or whatever spatial subdivision data structure that you have. Let's say there's n scattered nodes. We're going to divide these scattered nodes up into overlapping stencils, right? So notice in this picture, the green dashed line and the red line, both of them overlap. That's fine, right? And so for the rest of this discussion, let's focus on one stencil, just one stencil, which is the node x1, and its little n minus 1 nearest neighbors. all this is only useful if little n, the stencil size, is much less than the total number of points given to you. And now let's say that we want to approximate some linear operator, again, that script L, on just this one stencil P1. So the idea is to form some sort of approximation using translates of radial basis functions. In this particular case, we pick the radial powers because then there's, the parameter, it actually is not hard to tune and doesn't actually even need to be tuned. There are formulas for selecting them. So some linear combination of radial powers plus some linear combination of whatever your favorite polynomial basis is. Here, in more than 1D, I use tensor product Legendre polynomials. You could use literally anything. As long as the basis is well behaved, it should be good. Okay. In this case, we typically do polynomials in the total degree sense. So let's say L is the total degree and there's M basis functions where M is L plus D, choose D. We pick N based on the number of polynomial terms. And so we say the stencil size is twice the number of polynomial basis functions. The W sub K is super 1. There's N of them. Those are the RBF FD weights for the stencil center X1. Okay. How do you actually find these weights? I'll show you in a second. But the point is that people in the literature have shown that these are actually sometimes orders of magnitude more accurate than straight up polynomial least squares or moving least squares, which is sort of why we used it. We also used it because I'm an RBF guy, and that's the thing I know. You can actually find these weights.
Varun, I have a question here.
Yes, please.
So the setting is that all these points are fixed. In other words, you don't allow to have an adaptive refinement and so on, because that will break the bank.
Yeah, but we've done that too. I'll get to it.
Okay.
We didn't do it for the pin setting, but we have settings where we actually generate these finite difference weights on moving domains with adaptive sampling. You can do it in pretty much real time, at least in 3D.
Okay,
so it's not bad. The thing that lets you win is that the thing that lets you actually do adaptive stuff is that these are completely local and embarrassingly parallel operations, right? So I can compute the weights for each stencil independently of every other stencil. So it maps well to shared memory, GPU, even sort of traditional domain decomposition, MPI plus GPU sort of things can be done. So maybe we should come back to that because that's one of the generalizations at some point, at least in the pin context, that I would like to talk about. But just sort of real quick before I forget, let me just point out that you can compute the weights by solving a small, like an n plus m by n plus m dense linear system on each stencil. So you solve a bunch of local linear systems and get a global sparse matrix as a result. Now, this is all kind of messy, but the thing I want to point out here is that if you look at this block, so first of all, look at the upper right block here. This is a rectangular van der Waals-like matrix, which contains evaluations of whatever polynomial basis you have. So let's call that P for now. This guy is P transpose, right? So if you look at what's going on here, we really have a product of P transpose times the W's matching derivatives of the polynomials. In other words, we enforce that the weights applied to polynomial basis functions exactly recover derivatives of the polynomial basis function. So you build in the polynomial recovery or polynomial reproduction into this linear system. What do you do with the other weights down here? Well, you don't need them, you throw them away. They're Lagrange multipliers that enforce the condition that we reproduce polynomials exactly. Okay, so if anyone has any questions on that, I'm happy to explain further. Okay, so this is how you would actually sort of implement this. It turns out that the polynomials actually regularize the RBF coefficients, and even if the RBF block, which is the block with all the radial powers, even if that's kind of ill conditioned, this overall matrix, this block matrix, is easily invertible using Gaussian elimination or LU or whatever technique you like to use. But remember, it is dense on this stencil. So this is one stencil. You repeat this procedure for every stencil, and you sort of get finite difference weights. You can collect them all into a differentiation matrix, capital L. So each interpolant in traditional approaches, each interpolant populates a single row of that global sparse differentiation matrix. You can sort of do the complexity analysis and show what the cost is here, right? So, and think of all of this in the big O sense. Each interpolation matrix is n plus m times n plus m. There's one LU decomposition, which is n plus m cubed, and one backsolve, which is n plus m squared. And then there's n such stencils, so it's the product of all those things, right? So it's n times, I've done some factoring out here, but really for a fixed stencil size and fixed polynomial degree, this quantity that I've underlined scales as order n. So this it's pretty easy to, that's what we actually see in practice also, but it's order n with somewhat large constant. And so as George was saying, like, well, what if you're doing something adaptive? What if points are moving? This sort of led me to think about, okay, how do I reduce the constant size, right? How do I speed up these weight calculations? Is there something more efficient I can do? And the idea that I came up with, this was back in 2017, was to use each local RBF interpolant to not just compute weights for one point, but for multiple points at a time. Okay. And this I call the overlapped RBFFT method. We've been using it to a fair bit of success for some fairly complicated problems. Let me just illustrate what it is. The details are not highly important, but it's worth discussing because this is what we're using for DT pins. So in sort of traditional RBFFT, the red point here and this, or the filled circle and the empty circle, might get their own stencils. In overlapped RBFFT, if they're close enough, we might use the same neighborhood, the red points neighborhood, to compute finite difference weights for both the red and the green point. So in other words, our differentiation matrix will have a combination of mostly centered weights and some slightly one-sided weights. Of course, we should be cautious when we say centered and one-sided on point clouds, but hopefully everyone sort of gets the visual intuition here. These two might share the same stencil. In the new method, in the old method, they might have different stencils. So the idea is really simple. If you compute weights for one point using a stencil, don't ever find another stencil for it. Don't ever compute weights again for it. So the number of stencils, even though you have the same number of weights as there are, you have weights for every single point, the number of stencils is actually fewer than the number of points. Now, why does this actually give you any speed up? Because you're basically trading off a couple of things. You're doing more backsolves per stencil, more quadratic work per stencil, but since there are fewer stencils, you're doing less cubic work, right? So you're sort of tackling the bulk of the cost, which is the n cubed sort of cost, and you're trading that off by adding more n squared cost. And you can imagine you shouldn't do this everywhere in the stencil. You should do it in some small neighborhood around the center. And then the n squared is actually not as bad as n cubed itself.
Hi Varun, this is Amir.
Hey Amir.
Just one question.
Sure.
So when you choose these point clouds around a point, so for example, you are doing it for the boundaries,
yes,
then isn't that increases the dimensionality of the problem? Because basically, if, say for example, just 1D boundary, you are actually giving a cloud point which actually is in 2D, in 2 dimensions, right?
No.
Or they are still one dimensions?
No, yeah, there's no increasing the dimensionality. But I thought what you were saying is, as you go to higher dimensions, there'll be more points filling the volume, and so there is an issue with cursive dimensionality, but it's not in the sense that you're saying. So you still, like, let's say you're in 3D, you just grab a point and grab its nearest neighbors. That's still a 3-dimensional operation.
Okay. Yeah, got it. Thank you.
If you're on a surface, you grab a point and grab its nearest neighbors on the surface.
But this is for say for the collocation points, but for boundary points where you are doing differentiation, say for example, Robin
Oh, I
boundary,
see.
Norman
So,
boundary.
oh, yep. But that's I see what you're saying. So you're saying we don't just use neighbors that lie on the boundary. We also use neighbors in the volume. Yeah, but that's true for all traditional numerical methods, right? You use neighbors that extend into the volume. If you don't, you will get solution decoupling between the boundary and the interior. Right? That like this is true for, in some sense, this is true for finite elements, because for imagine an element sitting on the boundary, part of it is sort of lying along the boundary curve, the rest of it juts into the interior, right? Same for finite volumes, really any method. So this is not that different from numerical methods that we're all familiar with. But yeah, you're right that you don't just use boundary points. You use a combination of boundary points and interior points. And that's a good thing, in my opinion.
Thanks, Varun.
Yeah, of course. Okay, so the idea is, okay, so just remember that we had this linear system before. The idea is that with this new method, we'll just slap on a few more columns to the right-hand side for whichever points in that stencil for which we want to compute weights. So now each stencil is computing more weights than just at the center. It's computing in some neighborhood around the center. The question is, if you're doing this, you generally, in finite difference methods, you know that the weights at centers of stencils are well behaved. We don't know how well behaved they are further away from the center. And so we need some way to detect and discard undesirable weights within a stencil. So let's assume the weights at the center of the stencil are the best. If we come up with some sort of stability or quality indicator for weights at points away from the center of the stencil, still within that stencil, we can then sort of decide whether they're good or bad. Okay, so it turns out there's actually some really simple stability indicators that one can use. So the first one is just sort of the Lebesgue constant, or the Lebesgue constant associated with that weight vector. And I should really say Lebesgue function associated with that weight vector. So going back to this picture, let's say the red guy, the filled circle and the empty circle, we're computing weights for both of those. The filled circle is the center of the stencil. The empty circle is slightly off. Each of them has their own weight vector in the stencil. And so you take the empty circle's weight vector, you compute this Lebesgue function, which is just the one arm of the weights of the weight vector, and then you compare it and make sure that it's not larger than the one at the center. That's it. That's one stability indicator. We know sort of we know this has an important role in polynomial approximations. The Lebesgue function and the associated Lebesgue constant they're sort of known stability metrics in the RBF and the polynomial literature. So this is not a crazy idea. It's just a way of measuring how sensitive the weights are to the point locations. The second stability indicator is an oscillation indicator inspired by RBF theory. But the idea again is that it's very straightforward to compute. You basically take the weights and you take the dot product of the weights and the appropriate column of the right-hand side from here, corresponding to that weight vector. What this basically does is it numerically differentiates the RBF and polynomial basis functions, and the magnitude of that derivative tells you how much the weights are oscillating. And so basically we've used this to great success to decide what weights are good in this stencil and what weights are not. And so all we do is sort of loop. So if you're doing low order methods, I should mention, it seems to be the case that the Lebesgue indicator is sufficient. But if you're doing high order methods, they tend to, there's more weights, so there's greater potential for oscillation. And so you need some sort of oscillation indicator. So you can think of this as analogous to the Vino oscillation indicators that people have come up with. This you can think of as approximating an integral of some sort. The theory does sort of show that. Here's a visual schematic. So this is some stencil near the boundary of some domain where there's some boundary refinement. And this basically this is a fairly large stencil. This is a second order method. This is the stencil for a 6th order method. Both, I think we were approximating the Laplacian. As Ameya pointed out, the stencils extend into the domain. So the boundary is this last set of points here. Notice the Lebesgue function indicator says all these weights are good. The values are colored by, or the points are colored by the Lebesgue values. The oscillation indicator actually agrees that 2 of those points are good. And so we only pick weights for those points where both indicators say they're good. Okay. Notice for the higher order method, the oscillation indicator picks a subset of the points picked by the Lebesgue indicator. So the Lebesgue indicator is not sufficient. You also need the oscillation indicator to find the weights. I don't want to spend too much time on this, but I'm happy to answer more questions about this later. All you need to know for now, all you need to keep in your mind for now, is that we actually do less work than computing weights for each single point using its own stencil. And so how much less work? Well, if you look at this, if you compare one stencil per point versus using multiple points, using one stencil for multiple points, you can get high speedups in assembly as high as 60x. So this addresses some of what you were saying, George, that this can be expensive. Basically, you can build a differentiation matrix even without any parallelization in high dimensions fairly fast using this approach. And the weights are well behaved also. But the idea here is you don't need, there's no tuning parameters except the order of approximation that you care about. Sort of everything follows from the order of approximation. All you need to do is loop over all the points or parallelize over the points and compute weights as you go along. This is still order n, but with a much smaller constant to build that differentiation matrix. We've also shown, and I don't want to go over this too much, but we've also shown that the number of stencils actually, the number of stencils needed for n points actually is much less than n as you crank up the order of the method or as you go up to dimensions. You're not completely getting rid of the cursive dimensionality, but you can ameliorate it a little bit. I also want to point out for those of you doing polynomial approximation, I mean, if you're really worried about cursive dimensionality, you don't have to use total degree. You could try something sparse here, sparse recovery, or maybe you could use hyperbolic cross terms, sparse grids, whatever, right? All the tricks from polynomial approximation. Okay. The point I want to make here is that you can build these differentiation matrices pretty quickly, even though it's a pre-processing step for a problem where you have fixed points. If you're doing something adaptive, you can still build them very quickly in a neighborhood where you're doing adaptation, which is what we usually do. It's also common in RBFFT methods and in traditional finite difference methods to use ghost points. This is just some set of points outside the domain so that the boundary stencils are less one-sided. This means that our collocation node set actually has interior boundary and ghost points. You usually use as many ghost points as there are boundary points. And so if you add extra degrees of freedom outside the domain, meaning more unknowns, you have to add more equations. So we enforce the PDE at both the interior and the boundary points, and the boundary condition loss at the boundary points. I should quickly mention, we tried doing this for vanilla pins. It did not help on the Poisson problem, but it seemed to help with the heat problem, meaning we got lower errors and slightly faster training when we used ghost points with vanilla pins. But it seems problem dependent in the context of vanilla pins. For RBFFT and the discretely trained pins, we will always use ghost points. So for the Poisson problem, build a differentiation matrix for the Laplacian, let's call it L. Build another differentiation matrix for the boundary operator, let's call it B, right? These are the dimensions of these matrices. And we use 64-bit floating point to compute these finite difference weights as a pre-processing step. So this leads me to the idea of discretely trained pins. We're just going to take the vanilla pin loss over here, this equation up here, and we're going to write it using these differentiation matrices. It turns out it's more convenient to express these as fully discrete loss functions. You can see now the loss vector, which is still a function of the weight vector, in the mean squared error sense, is some differentiation matrix times the neural network evaluated at interior boundary and ghost points, plus these extra terms coming from the PDE. Similar thing for the boundary conditions. There's some boundary differentiation matrix times the vector evaluated at interior boundary and ghost. Okay, so the continuous loss function is written in this fully discrete sense because we have a bunch of matrix vector multiplies. I want to mention though, these are sparse matrix vector multiplies, right? Not dense ones. So you replaced all autograd operations, all spatial autograd operations with numerical differentiation just in this one slide right here. So is that it? Well, not quite. The problem is if you want to sort of minimize this guy with respect to W, you have to be able to take gradients of this whole term with respect to W, right? And so, okay, let's say we want to actually differentiate this with respect to W, and let's say this W is constantly changing. As Josh pointed out, maybe that's going to be expensive because you'd have to recompute weights. For now, let's just say we'll use autograd for this part of the operation. So don't use autograd for spatial derivatives, but use it for W derivatives. How do you use autograd for W derivatives when you have a matrix vector product? Well, let's just focus on LU minus F, that term, for simplicity. And let's ask ourselves what the gradient of that with respect to W is. Well, that is the gradient of it with respect to U, and then times the gradient of U with respect to W. Right? So now I just want to walk you through the set of decisions we made and why we made them. L and B are sparse matrices. It makes sense to store them in some appropriate sparse format. We picked compressed sparse row. But then once we picked compressed sparse row, it turned out that PyTorch support for CSR compressed sparse row matrices on the GPU was kind of limited. It wasn't actually, it was having certain troubles. This was several months ago. So we said, okay, let's switch to CuPy, which is the CUDA Python, a Python interface to CUDA for the sparse matrix vector multiplies. And then let's use DLPack to ensure that CuPy and PyTorch share the same CUDA context. Unfortunately, when we switched to CuPy, we found that PyTorch's autograd doesn't natively understand how to differentiate CuPy sparse matrix vector multiply outputs. So we ended up going down the rabbit hole here. Luckily, we realized, oh, it's not that hard to write a custom autograd for CuPy matrices. And we did all this in PyTorch. PyTorch lets you write your own autograd function. All we had to do is supply this first term in this, essentially this product rule or chain rule, right? And so the derivative of this matrix vector product with respect to the output layer of the neural network is just L transpose.
It's me, Varun. This is Lulu from Japan. So have you tried TensorFlow? Because we have done another version of ping called FPing, the ping for fractional PDE.
Right.
Because it's fractional PDE, so we also have a sparse matrix times the U. It's a global PDE. Right. And in PyTorch, in TensorFlow, it supports the sparse matrix, and it has nice AD. So we don't have any issue for sparse matrix.
It would have. You're right that if it switched to TensorFlow, we wouldn't have run into that issue. But Ram was mostly a PyTorch expert, my collaborator Ram. And so we wanted to stick with PyTorch and make it work in PyTorch. And we kind of managed to do that. All we had to write was this one operation. So we just had to supply this one piece of the autograd. So in the end, we just had to supply L transpose times grad WU, right? And we already have L. So this product is actually trivial to compute. So it wasn't too bad, but I didn't want to sort of go through. You're right that if it switched to some other framework, it might have been easier. Yeah.
Okay, got it. Okay.
Yeah, luckily it wasn't too bad. We were still able to get sort of the benefits of GPU parallelization. Once we realized that we only need to supply L transpose to PyTorch. PyTorch then we could then express this matrix vector product as another CuPy CSR SPME. And so let me point out there's two spatial autograd operations, and we replace them with two matrix vector multiplies. And then you can imagine for each of these terms, there's an autograd operation with respect to W, and we've replaced most of it with another pair of sparse vector multiplies, sparse matrix vector multiplies. Okay, so we have a total of 4 per training step, 4 SPMV operations. This last piece is still done using AutoGrad, but PyTorch just gives you that. And so we don't completely replace AutoGrad, but we've sort of tweaked it to work for our problem. Okay. You do something pretty similar for the heat equation, except that you also have to enforce the initial condition. Here we're doing the variant where we're actually doing continuous time identification. And so we're doing AutoGrad in time and RB50 in space, just to show that you don't have to discretize every single thing. It is mostly beneficial to discretize higher order derivatives. Okay, so we kept things really simple. We divided up time into even intervals, so even slices. And then we ordered all our math so that all spatial evaluations happen first on each time slice, and then we go to the next time slice. If you order things that way, then you get these sort of large vectors where the differentiation matrices multiply the correct quantities. If you order via time first and then space, the differentiation matrix operations become a little more complicated to write out, but I imagine you could do it with the same efficiency. Okay, I don't want to spend too much time on this. If someone has questions, I'm happy to come back and explain each term on the slide. But essentially, the idea is the same. Replace boundary condition, replace spatial AutoGrad operations with matrix vector multiplies, and then just sort of turn the crank to see what else needs to be done if you do that. So we needed custom AutoGrad for this also, but we could just use the custom AutoGrad that we wrote for the Poisson equation to handle the heat equation case as well. If no one has any immediate questions, I'll jump into the results because this is the actual fun part. Okay, so the first test we did was to compare AutoGrad versus RB50. So let me make it clear. We pre-computed the RB50 differentiation matrices for the Laplacian for different orders of accuracy. And so this means different polynomial degrees and different stencil sizes. We did second, third, fourth, and fifth order, and we did all this in FP64. We then took a deep neural network with random weights and tan H activation, and then we just kept increasing the number of layers, computed its AutoGrad FP64 Laplacian. So this is the most accurate Laplacian you can get for the neural network. And then we also computed the Laplacian using FP32 AutoGrad, and then we compared both of those to RB50. And so FP64 AutoGrad has basically error on the order of machine precision for this problem. And so we said, let's set that as the gold standard and let's compare everything else to FP64 AutoGrad. So here you can see the black line with the stars. That's actually FP32 AutoGrad. I mean, measuring relative error in computing the Laplacian as a function of the number of layers in the network. So we go from 1 to 10 layers. You can see basically if you use a low order differentiation for RB50, so second order, it's not as accurate as AutoGrad. But if you go third order and higher, it's pretty good. It matches in accuracy or even surpasses accuracy. Of course, it had better because FP64 has more digits of precision than FP32. This is not surprising, but it's also reassuring in one sense that, okay, we will not lose accuracy if you go sufficiently high order. On the right, we have a picture of time versus network depth, the time taken for AutoGrad versus network depth. And so you can see for FP64 AutoGrad is quite slow compared to FP32 AutoGrad. And so when we're using AutoGrad, we're forced to use FP32 for machine learning in general if you want any kind of speed. But notice how the RB50 costs for all the orders, second through fifth order, are mostly constant with network depth. They're going up like extremely slowly, but really they should be constant because the weights don't depend on the network depth at all, right? The weights just depend on the locations at which you want weights, at which you want derivatives. So this is not surprising that the cost is constant. It is nice that the cost is less than both FP32 and FP64. If you did something like the biharmonic operator, you can see that even fifth order methods are not sort of as accurate as FP32 AutoGrad, but they're probably good enough. You could always go higher order if you wanted. We only tested until order 5. But what I would like to point out is, at least in PyTorch, because of the way they've implemented AutoGrad and most machine learning libraries except JAX, the the cost has gone up exponentially when you're trying to approximate the biharmonic operator. And it'll go up.
Varun, you're right, because we have done the test, Siemens has done a test, and for jacks, it stays flat. Very
Yeah, I know.
accurate
I saw
flat,
that paper. Yeah, I saw that paper that in jacks, it's actually just like completely flat.
Yeah,
it's really cool.
we have our own test. We didn't publish it, but it's totally very accurate. Actually, we solve a UXXX equals 1, and you cannot do that with AutoCAD in PyTorch or TensorFlow, but jacks give you the great answer and also flat like you have. Yeah.
Yes, exactly. And I acknowledge that, and that's because JAX uses this this new technique from 2019, right? The Taylor mode differentiation idea, which is where instead of generating stuff recursively, they use some sort of Taylor expansions to compute the autograd. And so, yeah, in something like that, you would expect something flat, but in PyTorch, you can imagine sort of things are going to get worse with each higher order derivative. I will get back to this because I don't think, so you could then say, well, why do any of this? Just move to JAX. I think we're getting a benefit beyond just the speed up from beating autograd. And we'll get to that in a couple of minutes. So let's take some simple test cases that we can intuitively understand and work on those. So this is the 2D linear Poisson equation. I have a node generator because I worked with meshless methods. And so we just put down some quasi-uniform nodes on the domain. We manufacture a solution. In this case, we're using Robin boundary conditions and sines and cosines, 1 plus sine times cosine as the solution, which I plotted here. And we're going to just measure relative error against the solution for vanilla pins in both FP32, FP64, and for discretely trained pins, which are traditional pins using RBFFT for spatial derivatives. So this is FP32 DT pins against FP32 vanilla pins, FP64 vanilla pins. On the rightmost panel, you see relative errors. The vanilla pin errors are lower, fairly lower than all the RBFFT errors. Okay, so this is where the neural network was trained in FP32, but the RBFFT weights were computed in FP64. Okay, the errors are, you notice they're sort of messy and they're higher than all the vanilla pin errors. However, you do receive speedups, right? You just by moving to the differentiation matrix, you do have a reasonable speedup, and depending on the problem, maybe this is good enough for you if you're willing to sacrifice, some accuracy. So I think the maximum speedup here, where the accuracy is also reasonable, is something like 3x, right? But we looked at this and we said, okay, what if we did FP64 discretely trained pins versus everything else? And now the moment you go to FP64, you notice that all the high order methods, or almost all of them, line up almost perfectly with both FP32 vanilla pins and FP64 vanilla pins in terms of error. They match it dead on. In some cases, they're a little lower by like, 1 digit in like the 4th place or something, but they're pretty much the same curve. But notice that we still actually get a speed up. So we get something like 2 to 4x speed ups, even though we're using FP64 on the GPU with discretely trained pins. This kind of confused us because, first of all, FP64 is supposed to be not as fast as FP32, right? There's on GPUs. GPUs have improved a lot, but there's still a discrepancy in speed between them. So we said, what could be the source of the speed up? And so we said it can't all be explained just from autograd, because if you look down here, the difference in time taken for autograd versus RBFFT is not, it's not that different, especially as you go deeper into, as you make your network deeper. And so we said, okay, let's try and tease out what exactly is giving us the speed up. And so here, I'm actually plotting the number of epochs versus the training set size, or the number of collocation nodes. Up here, you can see the 2 curves in both graphs up here. So on the left, we have FP32 DT pins. On the right, we have FP64 DT pins. The 2 curves on the top of these graphs are the vanilla pins, FP32 and FP64 vanilla pins. And you can see they actually take more epochs than the discretely trained pins to reach the lowest relative error. Okay, so notice the axis is scaled by 10 squared. So these vanilla pins actually take about, on average, twice or thrice as many epochs as discretely trained pins to reach their lowest relative error, which sort of explains a 3x speed up. Right? There's basically somehow by switching to discrete training or by numerical differentiation, we've got fewer epochs to reach the lowest relative error. And so on the left is FP32, on the right is FP64. In FP64 DT pins, you're actually seeing a trend where the number of epochs is kind of reducing with n for the higher order methods. Okay, so the question is why? Why do discretely trained pins need fewer epochs? We don't know yet. To be honest, right, this is not something we know, but we can make some reasonable guesses or try and reason about this. What changes?
I have a question.
Yes, please go ahead.
Sorry, this is Michael.
Hey.
So for the epochs, what do you are you defining like a? Maybe I missed this. Is it like atom or LBFGS? Are you defining
yes.
like when it hits a termination tolerance to determine how many epochs it takes, or what?
Yeah, sorry, I should have mentioned that. Yeah, we're using LBFGS.
Okay, so that's the amount of epochs until it terminates. Okay.
Well,
okay,
no,
thanks.
it's the number of epochs taken to reach the lowest relative error.
Okay.
Yeah, which doesn't mean it'll terminate, but it could oscillate around that for a while, right? But yeah. It's the number of epochs taken to reach the lowest relative error. Yes. And yeah, so we can sort of try and reason about this. We can ask ourselves why DT pins take fewer epochs. One possibility is that because when you do numerical differentiation, so let me rephrase. When you do numerical differentiation, your loss function is a combination of the neural network values, a linear combination of the neural network values. It is not the analytical derivative of the network. Maybe a linear combination of the neural network values is just easier for LBFGS to minimize. This is one possibility. The other possibility is somehow the autograd loss functions have either a larger null space or more local minima than the discrete ones. We don't quite know. We haven't analyzed this. We just sort of, because this work was a conference submission, we just sort of tried to tease out what the source of the speed up was, but we don't quite understand why it takes fewer epochs for numerical differentiation. We're confident that this effect is real, though. We just haven't figured out why yet. There's another question. Is this just problem dependent? Are discretely trained pins always as fast, or are they slower? Is this just a 2D thing? So we said, okay, let's try nonlinear Poisson, where now you have the exponential term e to the u term. So this is nonlinear in u, not nonlinear in the differential operator. And here, we no longer have those 3x speedups. The speedup drops to somewhere between 1.5 to 2x. Basically, the nonlinear term is taking up more training time than the differential operator in some sense, right? So discrete training seems to help when the differential operator contributes significantly to training time, but maybe not when you have other terms that are dominating the training time, right? You can make an engineering choice here, sort of based on what you know about the problem that you're solving, if you know something. I have some preliminary 3D results also in the ball. And so this is a bunch of quasi-uniform collocation points in the ball. You can see the points on the surface of the sphere. They're not quite uniform, but they're pretty close to uniform. We manufacture another solution, use Robin boundary conditions. And now we compare this time I'm just comparing the higher order versions, leaving out the second order version just because it's not that good, against FP32 vanilla pins. You can see we reach roughly the same relative error as vanilla pins. In some cases, we're lower, slightly higher in others, but we maintain our speed ups even in 3D. And notice the x-axis has the training set size. And so we're maintaining our speed up as we go up in the number of training points. We also did space time. And in this case, as I pointed out, we did autograd in time. And so we have just one set of spatial points, which is about 800 of them, I think, roughly. And then we have 25 time slices. So there's a 20,700 space-time collocation points. And here, we sort of just compared discretely trained pins in FP64 to vanilla pins. This time I'm plotting relative error versus order of accuracy. You can see as soon as you go to third order, we match accuracy with vanilla pins, and we sort of have our speed up somewhere between 2 and 2.5x. These are not, in my opinion, these are not like mind-blowing results, but it's nice to have speed up without having to go to a more powerful GPU. And if you went to a more powerful GPU, you would still get a speed up there, is my my guess, because we're nowhere near being memory limited.
Varun, it would be interesting to show us if you have the loss functions to see if the loss function is smoother with the finite difference with these DT pins. Did you pay attention to that versus the vanilla pins? The history of the loss function, yeah.
Yeah, so I don't have those plots right here with me, but we looked at those, and I can tell you something about it. Basically, what we saw is that the actual loss functions, right? LU minus F and Laplacian U minus F, right?
Yeah, because that's how you decide on the number of epochs, yeah.
So we didn't visualize the loss function itself, but we sort of calculated those terms as a function of the number of training epochs. And basically, we saw that the discrete residuals would drop faster.
I mean the history. Yes. Not the landscape will be difficult, although it's possible. But
exactly.
But the history.
Yes. So when we were doing the history, we saw that the discrete losses dropped faster and lower before even they level off. They all level up eventually.
But there are no fluctuations. That's what Mike also asked before. There's no fluctuations.
No, not that we saw. No.
Okay.
Yeah, there's something about this that's where we seem to be smoothing away fluctuations in the loss just by switching to discrete differentiation. I'm not sure why though. Because you could say things like, oh, maybe it's damping from the differentiation, but we use high order differentiation, right? So there's not that much inherent damping built into that. So yeah, we actually don't know why. And George, I'm happy to share those plots with you. I have them in a folder buried 4 levels deep somewhere. Okay.
Thanks.
Yep, of course. So just to summarize, both FP32 and FP64 DT pins were faster to train than FP32 and FP64 vanilla pins on the problems we tested, right? DT pins are faster than FP32 vanilla pins on the problems we tested. High order accuracy does seem important. It depends on what you call high order. Definitely higher order than 2 seems to be needed. And depending on the operator you're approximating, going as high order as you're willing to go seems to help. FP32 DT pins are not as accurate as any of the vanilla pins, but FP64 DT pins are without any loss in speed up. This tells you that the speed up is not just from going to FP64 or something. In fact, there is no slowdown from going to FP64. The loss functions are just somehow nicer, right? So yes, there's a sparse matrix vector multiply, but the objective function is somehow easier to minimize. My hope, then sort of wrapping back to JAX, my hope is that this means that we'll somehow still see speed ups if we move to JAX, because it's not just from beating AutoGrad, it's also from having a better loss function. This is my hope anyway. We won't know until we test more complicated PDEs, but I'm reasonably confident that we're onto something here. So just to comment on a bunch of things that we've thought about, but not started working on. We know, I'm fully aware that these results just scratch the surface. This is just the beginning of a series of exhaustive tests. So we're still doing 3D testing. We think this will help a lot with G-pins because you're computing those third order derivatives. We might get further speed up and further simplification of the loss functions if you use discrete G-pins. I think that because the discrete training approach is sort of orthogonal to all these existing techniques, they could be combined as you wanted with those existing techniques. So for instance, you could combine them with X-pins, with C-pins, DepotNet. One thing we did not try that I would be interested in trying is other activation functions, right? So what if you use something like your Rowdy activation functions, those tunable ones? How well would this approach work with that? My suspicion is that as long as the activation function is sufficiently smooth so that the high order differentiation doesn't produce numerical issues, we should be okay. If you use something like ReLU, I think you need a limiter because you'd get Gibbs oscillations when you try to differentiate a piecewise smooth function with some high order method. I should also point out that this approach should just work almost out of the box on surfaces. And so, in RBFFT, you don't need to project solutions onto surfaces. You can build a differentiation matrix L that directly incorporates, that directly measures the derivative on surfaces. And so you might just actually be able to use the same loss function with a different L and, if necessary, B to get PDEs on manifolds. I also want, I'm almost done with my talk. The relevant publications, this particular work is currently under review. We have a bunch of papers on solving RB50. We have one paper on solving RB50 and moving domains, one on fast node generation, and then this older paper where I came up with the overlapped RB50 method.
Was a good candidate. But any more questions for Varun? That was very clear. Varun, thank you very much. Lulu is doing GPINs with, he did his GPINs with a high school student.
Oh, wow, that's awesome. Ram, he's younger than you.
Yes.
I think so, yeah.
Lulu, what do you think of using this for GPIN? I know JAX would work well, but this one also.
Yes, I agree. So for standard pin, maybe it's not, the speed up is 1.5 or 2. But for GPIN, definitely we'll have much more speed up.
Yeah, I mean, we got
even higher derivatives.
Yeah, we got 4x in some problems, but you're right that depending on the PDE, it's probably better for GPINs than it is for standard pins. Yeah.
Yes, yeah, that's I agree. I think GPIN would be a good direction.
All right, we should talk. I mean, we can just give you differentiation matrices and you just plug them in and see what happens.
Zogren?
Hey, Varun, I had a question. This is Raj from Brown.
Hey.
It's not question, just comment actually. So most of the comparison you showed, that is against the number of training points.
Yes.
But complexity of really depends on the number of vertices and edges, like what is the depth and the width of neural network. So did you try that, measuring your performance over that?
Yes. So these didn't make it into the graphs and the final results, but we tried different neural networks with different width, different depth. Basically, the autograd test is indicative of what one would expect. There are some neural network architectures that seem to produce lower errors than others. We've all seen that, right? There's some magic numbers that seem to produce better results. But in general, the speed up seems to stay. Because it's somehow about the optimization function or the objective function that you minimize.
That I'm talking in terms of the wall time. Not
yeah, right. And yeah, since the speed up stays, the wall time is improved also. Yes.
Okay. Thank you.
Yeah.
For the talk room. And yeah, this is it for this week's seminar. So everyone has a good weekend. See you next week.